A hydrogen truck can refuel in minutes. That sounds simple, almost like pulling into a normal fueling station and connecting a nozzle. But behind that simple moment is a much bigger industrial system. The truck is only the visible part of the story. The real machine is everything around it. Hydrogen production, compression, high-pressure storage, pre-cooling, dispensing, safety controls, fleet scheduling, and corridor planning. Without that system, the truck cannot operate reliably. So the real question is not only how to build a green hydrogen truck. The real question is how to build the infrastructure behind green hydrogen trucks. This is where hydrogen freight becomes more than a vehicle story. A diesel truck depends on a fuel network that took decades to build. A battery electric truck depends on grid capacity, chargers, substations, and depot energy planning. A hydrogen truck depends on an entirely new clean fuel ecosystem. It needs hydrogen to be produced, conditioned, compressed, stored, cooled, and dispensed safely at the right pressure and volume. If one part of that chain fails, the truck may be ready, but the system is not. That is why the infrastructure behind the truck matters as much as the truck itself. A hydrogen refueling station is not just a fuel pump. It is a small industrial plant. Inside the station are compression systems, high-pressure storage vessels, electrical equipment, cooling units, control systems, leak detection systems, safety systems, and dispensers designed for heavy-duty vehicles. The pump that the driver sees is only the final interface. Behind it is a complex system built to move hydrogen from supply to vehicle safely and consistently. This is one of the most misunderstood parts of hydrogen trucking. People often imagine the station as a simple version of a gasoline station, but in reality it is closer to a controlled industrial gas facility connected to a logistics operation. The first infrastructure question is supply. Where does the hydrogen come from? For green hydrogen, the process starts with renewable electricity and purified water. An electrolyzer uses electricity to split water into hydrogen and oxygen. The hydrogen is then dried, purified, and prepared for compression and storage. This production step can happen on-site at the station, near a logistics depot, or at a larger central production facility that delivers hydrogen to multiple stations. Each option has trade-offs. On-site production reduces some delivery needs but requires power, water, equipment, land, and maintenance. Centralized production can achieve scale, but then the hydrogen must be transported to where trucks need it. This is why hydrogen infrastructure planning begins with demand. If only a few trucks use the station each day, on-site production may be expensive and underused. If a large fleet refuels every day, dedicated production and storage can make more sense. The economics are not driven by technology alone, they are driven by utilization. A hydrogen station has fixed costs whether one truck fuels there or 50 trucks fuel there. The more trucks use the station, the more the cost can be spread across kilograms of hydrogen delivered. That is why fleet volume becomes one of the most important design variables in the entire system. After hydrogen is produced or delivered, compression becomes the hidden workhorse. Hydrogen must be compressed so it can be stored and dispensed efficiently. This step is energy intensive, technically demanding, and essential for fast refueling. The compressor takes lower pressure hydrogen and raises it to the pressure needed for storage and vehicle fueling. For heavy-duty applications, this can involve multiple compression stages, valves, gauges, cooling loops, and safety controls. The compressor is not glamorous, but without it, the station cannot deliver hydrogen at the pressure and speed required by trucks. Compression also affects reliability. If the compressor fails, the station can lose fueling capability. If it is undersized, trucks may wait too long. If it is oversized, the project may become unnecessarily expensive. This is why hydrogen station design must match real fleet behavior. How many trucks arrive per hour? How many kilograms does each truck need? Are trucks fueling overnight, during shift changes, or continuously throughout the day? Infrastructure must be sized around operations, not just around theoretical capacity. Once compressed, hydrogen needs storage before it can be dispensed. Storage acts as the buffer between supply and demand. A station may produce hydrogen steadily, but trucks often arrive in waves. A fleet depot might see several trucks fueling in a short period. Without storage, the station would struggle to meet peak demand. High-pressure storage banks allow the station to hold hydrogen and deliver it quickly when trucks arrive. This storage layer is what turns a production system into a practical fueling system. High-pressure storage also introduces another infrastructure challenge: safety and monitoring. Hydrogen is light, small, and highly mobile as a gas. Storage systems must be designed with proper materials, leak detection, ventilation, pressure relief devices, control systems, and operating procedures. In a well-designed system, safety is not an afterthought. It is built into the physical layout, equipment selection, controls, and maintenance strategy. For heavy-duty trucking, where stations may serve large volumes of fuel every day, reliability and safety must be engineered together. Fast fueling creates another hidden requirement: pre-cooling. When hydrogen is transferred quickly into a vehicle tank, temperature can rise during the filling process. To manage this, the hydrogen may need to be cooled before dispensing. This is why pre-cooling equipment appears in heavy-duty hydrogen stations. It is not there for decoration. It helps control the fueling process so trucks can refuel quickly while remaining within safe temperature and pressure limits. Fast fueling is not just a bigger hose, it is an engineered thermal management process. This is one of the most important ideas for viewers to understand. The promise of hydrogen trucks is not only range, it is uptime. If a truck can refuel in minutes and return to work, hydrogen becomes attractive for fleets that run long hours, carry heavy loads, or operate on tight schedules. But fast refueling only works if the station is designed for it. The station must have enough supply, compression, storage, cooling, and dispensing capacity. If the station bottlenecks at any point, the truck's advantage disappears. The next layer is fleet depot utilization. A hydrogen station becomes more valuable when it serves predictable demand. This is why depots, ports, logistics centers, warehouses, and industrial fleets are such important early markets. They create concentrated demand. Instead of waiting for random public customers, a fleet depot can schedule refueling, manage routes, and keep the station operating at higher utilization. This helps spread infrastructure cost across more fuel volume and makes the economics stronger. Fleet utilization also changes how the station is operated. A station serving heavy-duty trucks may need multiple dispensers, queue management, data systems, maintenance planning, and redundancy. If one dispenser goes offline, the fleet still needs to move. If one compressor is down, backup capacity may be necessary. If trucks arrive in waves, scheduling software can reduce waiting time. This is why hydrogen infrastructure is not just hardware. It is an operating system. The station must work with fleet behavior, not against it. Finally, hydrogen trucking cannot scale through isolated stations alone. It needs corridors. A single refueling station can support a depot or local fleet, but regional and long-haul freight require connected infrastructure. Trucks need confidence that they can refuel along the route, at ports, near warehouses, at intermodal hubs, and across major logistics corridors. This is where the hydrogen system becomes a network. Production sites, refueling stations, ports, rail hubs, distribution centers, and industrial clusters must be connected strategically. Building corridors is different from building random stations. Corridors focus infrastructure where demand is strongest and where trucks already move. They connect freight flows instead of scattering assets without enough utilization. A hydrogen corridor can link renewable hydrogen production to logistics parks, industrial customers, and ports. It can support drayage trucks, regional freight, warehouse distribution, and eventually longer routes. The goal is not to build everywhere at once. The goal is to build where the system can survive. This is the ReneEnergy system stress test. If fuel cost is too high, the truck loses. If station utilization is too low, the station loses. If compression, cooling, or storage is unreliable, the fleet loses. If corridors are incomplete, operators hesitate to adopt the technology. The winner is not simply the best truck. The winner is the best infrastructure system around the truck. Hydrogen freight will succeed only where engineering, economics, logistics, and utilization come together. So when we ask how to build the infrastructure behind green hydrogen trucks, the answer is not one piece of equipment. It is a sequence. First, secure reliable hydrogen supply, then compress it efficiently, store it safely, cool it for fast fueling, dispense it with precision, operate the station around fleet demand, then connect stations into corridors that match real freight movement. This is how hydrogen moves from a promising truck technology to a working transportation system. The truck needs a system, and that system must be engineered, financed, operated, and scaled with discipline. That is the real challenge behind green hydrogen trucking. Not just building vehicles that can use hydrogen, but building the invisible infrastructure that makes those vehicles useful every single day. At H2 Hub by ReneEnergy, we break down the engineering, economics, infrastructure, and project development behind hydrogen systems so developers, consultants, investors, and clean energy professionals can understand what survives beyond the hype.